Cynthia, how are you doing?
Hi, I'm okay, thank you.
Let me start to make sure I know how to pronounce. Do you want to check that your screen works?
Yeah. Can you see it?
Yes, now we can. Yeah, you'll just need to hit full screen. There you go.
Yeah.
Perfect. And we'll wait till precisely 8 a.m. to get started. It's about 3 minutes.
Sure. Oops.
Are you in Manchester right now?
Yeah, unfortunately, yes.
Ah,
I would have preferred to be in Los Angeles.
what's the weather like there?
Well, it's expected to rain non-stop until end of the month.
Can you send us some rain?
Oh, yes. We can exchange.
Yeah. Yeah, we could use some. Believe it or not, it never rains in August, but we had about 1/4 of an inch of rain the other day, which was unusual. But sometimes we worry that they're pyrocumulus clouds, which means the wildfires actually create clouds that pull water out of the ocean. So it's very strange weather conditions.
Rick?
Yes.
Can you unmute me?
You are unmuted. We hear you loud and clear. You want to just test your screen quickly, or?
Okay, sure.
Let me stop. Yeah.
Yeah, I think yeah, you won't have any trouble, Jeff.
Okay, yeah.
All right, we should go back to Cynthia then. And we're just about ready. As I said, I'll wait till exactly 8 a.m. All right, it's my great pleasure to start this plenary session. My name is Richard Kainer from the University of California, Los Angeles. And we have with us Professor Cynthia Casiraghi, who has won the Professor Alan Heeger Award. And this is a Young Investigator Award for somebody who's made outstanding achievements. And it's a special pleasure for me to be able to present this award in a sense, because Alan Heeger was my co-advisor in graduate school. So I wrote 5 papers with him. All right, Cynthia is a very dynamic researcher and is well deserving of this award. She earned her PhD in electrical engineering from Cambridge University. She was an Oppenheimer Fellow in electrical engineering. She was then a Humboldt Fellow in physics at the Free University of Berlin. And then she was a lecturer in graphene chemistry at Manchester. And now she's a professor in nanoscience in the Department of Chemistry at the University of Manchester. And she's going to tell us about water-based and biocompatible 2D material-based inks, from fully inkjet printed heterostructures to biomedical applications. So congratulations, Cynthia.
Thanks for the nice introduction, Richard. And of course, I want to, first of all, to thank the organizers for the award. It's a great honor, of course, to receive this award and to be included together with many super top leading scientists in the field. And so Richard gave already a very good introduction, so you know already I have a kind of peculiar actually background. I moved between different departments and in different countries, and so I actually have been very lucky because I've been exposed to different nanostructures, nanomaterials, different problems and challenges. For those who are not familiar about my research, I want to give a very, very short, I promise, overview on my research expertise. So I basically started my research by investigating ultra-thin carbon films that were used as a protective, actually are still used as a protective barrier for hard disk. And this was actually a project in collaboration with IBM many, many years ago when they still had the labs down in California, actually. And so I was studying the nucleation and the growth of these ultra-thin films, mostly by atomic force microscopy. And also I was in charge of characterizing the structural properties of these films. And this is where I started basically working with Raman spectroscopy. And therefore, I developed a strong expertise with this technique that I then applied to other carbon nanostructures, so nanodiamond, diamond-like carbons, carbon nanotubes, and of course, graphene and graphene-related materials. And we published several contributions where we demonstrated how powerful is this technique for the characterization of graphene and related materials. And today I'm still doing Raman spectroscopy, although not as a main, I would say, activity of my research group. We are applying Raman spectroscopy to one-dimensional, quasi-one-dimensional aromatic structures, meaning graphene nanoribbons produced by bottom-up approaches in the labs of Professor Klaus Mullen and Professor Xilian Feng in Dresden. And we are also applying Raman spectroscopy to study nucleation and growth of organic crystals, which is a new project which I may touch upon towards the end of my talk if there is still time. And my main research these days is about printed electronics and using 2D material for printed electronics, and by combining basically my background in engineering with materials chemistry and chemical and formulation chemistry. And so that's the topic of my talk. I'm going to talk about printed electronics made of 2D materials, but you will see that actually I'm interested also in applications where beyond the printed electronics. So we have very strong collaborations with biologists, for example. So we are aiming at basically exploiting these materials for biosensing, bioelectronics, and biomedical applications such as drug delivery. But I will explain more details later in the talk. Okay, so our goal is hopefully to establish in the near future a technology able to make fully printed integrated circuits where we can exploit the properties of 2D crystals and also other nanomaterials. And to do so, we want to basically make use of the heterostructure-based technology. And but we want to make heterostructures starting from solution processed 2D materials. And this has been already introduced by Mark yesterday, so I'm not going into too many details. And of course, I just want to remind you that the use of solution processed 2D materials will enable us really to exploit the full potential of an heterostructure-based technology, because in principle, we will be able to make heterostructure of arbitrary complexity, even including 20, 50 different 2D materials into our heterostructure in the sequence that we want. Something which is quite difficult and time-consuming to do with crystals produced by chemical vapor deposition or mechanical exfoliation. And of course, those kind of heterostructure can be fabricated with very simple techniques. And we have many approaches that have been already developed for us in organic electronics, so they can be easily extended to the crystals. And in particular, inkjet printing is a very attractive technique for fabrication of heterostructures, starting from solution processed 2D materials, because as you can imagine, we can print very thin films, which will be suitable for flexible substrates, so will be compatible with flexible electronics. In principle, we can make those heterostructure on any substrate, on any location on the substrate, and by simply printing different inks on top of each other. However, inkjet printing is actually not so simple as it looks like. And there are actually two issues that we need to remember when applying inkjet printing to the fabrication of heterostructure. The first issue is general issues related to the inkjet printing technique itself. And many of the printers that you will find in the labs are actually piezoelectric inkjet printers. And in this specific case, basically not all the inks will be inkjet printable. And so only the inks must have a specific rheological properties. And this is because the rheology, so surface tension and viscosity of the ink basically determine how the droplet is formed at the nozzle. And and in turn, this determines how well the material is deposited on the surface. And of course, the key goal to achieve when we use inkjet printing is to achieve a full control on how the material is deposited on the surface. Otherwise, we can use drop casting. And so certain inks are not suitable. And for example, water is well known to be a very bad solvent for inkjet printing. The surface tension is too high, the viscosity is too low. And so a water-based solvent will produce an unstable droplet formation, which is not suitable for device fabrication. In addition to that, we also have another issue to remember, and this is related to the fabrication of vertical devices. So it's very easy to use inkjet printing when you want to make in-plane devices, but for vertical devices, there is a problem we need to take into account, which is very well known in the community. So when we print one material on top of the other, the two materials will tend to redisperse at the interface. And this is obviously obviously very bad in terms of device fabrication, because devices obviously need very well defined and interfaces. So we cannot really produce devices if we are not able to control the interface between the different materials. This will affect the reproducibility and the performance of the device. So this problem needs to be mitigated somehow. And typically in organic electronics, people use the orthogonal solvents approach to mitigate this problem. However, this cannot really, be extended to 2D materials. And this is because, as you know, 2D materials dispersions can be produced only in a limited number of solvents. And I'm not going to go into the details here. I'm pretty sure everybody knows that in the case of defects-free graphene and other 2D materials, the typical solvents used in liquid phase exfoliation are NMP and DMF. So that means that NMP is not really a suitable solvent for the production of vertical structure. However, if we look at the rheology of NMP, actually NMP is perfect. It has a perfect surface tension and perfect viscosity for to be used as a solvent in an inkjet printer. And indeed, the very first inkjet printed device made with the graphene dispersions were actually produced was starting from NMP-based graphene dispersion. So it's possible to print with NMP, but NMP is actually not an ideal solvent if we want to really develop printed technology based on 2D materials. There are several issues around NMP. It's toxic, it's expensive, has a very high boiling point, so it's difficult to remove. It will leave a lot of residuals that are difficult to remove. On silicon, for example, as you can see from the picture at the bottom, we have a very strong coffering effect, and so the substrate will need to be functionalized somehow. NMP is also quite aggressive solvent, I would say, towards plastic, the plastic of the cartridge, the plastic of the substrate, and so on. So it became quite clear in the community that we needed to make new formulations for inkjet printing beyond the use of standard NMP. And many groups propose different type of formulation. This was also discussed by Mark yesterday, and many other groups in Europe and in Asia propose different formulations. And however, if we look at the compositions of the formulation, you will see that either the solvent or the additives used to make those formulations are actually quite toxic. And it would be nice, therefore, to produce inkjet printable inks based on water. And however, this requires to start the design of the formulation from scratch and to basically solve all the issues one by one. And so this is exactly what we did. So first of all, we started with the exfoliation of graphite and layered materials in water. So it's very well known that it's possible to exfoliate those materials by using stabilizing agents, exfoliating agents, typically surfactants or polymers. And however, in our case, we decided to use small aromatic molecules as an exfoliating agent. Indeed, if you look, for example, at this molecule here, you can see that this is basically a molecule that will work as a surfactant. We have an hydrophobic part, which is given by the pairing core, which will interact with the graphene through pi-pi interactions. And then we have the charged group here, which will enable electrostatic stabilization with the water. And while we were working with exactly this molecule, this paper came out, published by Professor Green, and showing a very, very nice comparison between exfoliation produced with traditional surfactants and polymers and this class of pyrene derivatives. And they show very nicely that although pyrene derivatives, they look like surfactants, actually the exfoliation is much more efficient compared to traditional surfactants and polymers. We can achieve a much higher concentration, which is obviously very important in terms of inkjet printing. And in addition to this work, we also demonstrated that exfoliation with PS1 is indeed possible, and with pyrene derivatives, and in particular with PS1, is also possible, and the quality of the material produced is extremely high. And you can see that we don't have any defects. And in the case of graphene, we don't have any carbon-oxygen formation. So these, although we work with water, this material has nothing to do with graphene oxide or reduced graphene oxide. And the approach can be used to exfoliate basically any layered material that is not reactive in water. So we can use it to exfoliate transition metadichalcogenides, boron nitride, and so on. And the flakes are really thin. So typically the average number of layers will be between 3 and 7, as you can see from the TM pictures, with obviously smaller amount of single layer and bilayers. And however, as I mentioned to you, water is not a good solvent for inkjet printing. So if you try to print those formulations as they are after exfoliation, then you will not get very good results. And this is indeed the picture that's showing the printed graphene, the very first attempt that we made by printing those formulations without any modification. And you can clearly see that there is a very strong coffee ring effect. The material is completely randomly distributed. The concentration is actually even too low. And the line will not even be conductive. So that means that we still have to perform some modification that can be done post-exfoliation. And so in particular, we know that water is not a good solvent because of its rheology, but then it's very easy to change his surface tension and his viscosity by adding some modifiers. And this is exactly what we did. We lowered surface tension and we increased viscosity by using certain additives, and at the same time we further increased the concentration by removing all the pyrene molecules that were not absorbed on graphene by introducing a further centrifugation step after exfoliation. And by basically introducing these very small tricks, we basically managed to have a printable graphene ink, and with a concentration that can go even up to 8 milligrams per milliliters, although we never use such a high concentration because it will produce neutral blockage. So typically by printing with 2-3 milligram milliliters, we will be actually able to get a conductive line even with one printing pass. So you can see that with those simple modifications, we've been able to actually produce an inkjet printable water-based ink. And however, we are still not ready to make fully printed heterostructure because, as I mentioned to you, there is another problem that we need to mitigate, which is the intermixing of the material at the interface. And this again can be mitigated by applying formulation engineering, and in particular by adding binder in the dispersion. So in our case, we decided to use a xanthan gum because it's water soluble, it's biocompatible, and shows a very strong shortening effect, which is exactly what we want here, because this effect will kind of minimize the diffusion of the flakes, and therefore will minimize this intermixing at the interface. And I want to specify that despite using these additives to change the rheology and to minimize this intermixing at the interface, the ink is still stable and the ink is still printable, as you can see from this picture here. The droplet formation is still stable. And this is because we include very, very tiny amount of additives in the ink. And so this process needs to be done very carefully. Okay, so with this simple modification of the inks, we have been basically able to produce inkjet printable inks of different 2D materials, and they are all printable. There is no unstable droplet formation. They can be printed for months and months in the same cartridge. There is no precipitation, reaggregation of the material in the cartridge. Typically, one will be able to print for at least 6 months with the same cartridge. And I want to mention here that we are actually collaborating with several groups where we are providing basically those inks, a couple of groups in US and several groups in Europe. And so far, nobody ever complained about the printability of the inks. So it's really a robust technology. And we've been able to print on different substrates, but I would say that our preferred substrate is actually paper. And the reason is obvious. As you know, paper is porous and it can absorb water very easily. And so when we print on paper, the solvent will be absorbed very quickly in the substrate. And so the material will not really have time to diffuse around, produce coffee ring effect, and so on. So by printing on paper, we can really deposit a very high amount of material in a very small area, and which translate in a very high resolution. And so, for example, here you can see a Nobel Prize medal that has been printed with our graphene ink. And you can see how sharp and nice are the features in this medal. And this is because we can really print with a very small resolution. On paper, we can go down to 8-10 microns, which is well beyond the nominal resolution of the printer, which is 50 microns. But more important, when we print on paper, because of this effect of the porosity of the substrate, we can actually minimize the sheet resistance. So as you can see in this plot here, we can achieve a sheet resistance below 1 kilo ohm per square by printing just few printing passes, so by printing on top of the same feature over and over. And this is achieved by printing under ambient conditions and without using any pre-processing or post-processing. So this is just the sheet resistance as it is. And of course, it's possible to decrease the sheet resistance further by performing post-processing. And this is actually what we did in a follow-up work where we wanted to perform whole measurements on these printed graphene films. So the idea was basically to get some indication on the doping of the film. Is this graphene film doped, and how much is the doping, and so on. And in order to perform whole measurements, we had to anneal at 400 degrees C. And at such a high temperature, all the additives that we use are basically boiling, so they should not be present anymore. And just the pyrene is boiling at around 400 degrees C. So maybe some pyrene will be left at that temperature, but most of the additives will be gone. And indeed, the sheet resistance dramatically dropped, and we were able to basically achieve around 20-30 ohm per square. And however, from the whole measurements, it turned out that the printed graphene film, even after such a harsh annealing, is actually still slightly hand-doped. Which was kind of surprising, and we think that this is due to eventually some pyrene residual that is actually trapped in the film. We don't think that is coming from the water. Typically, water will p-dope graphene, and in any case, the doping, if you look at the charge concentration, is actually very small. And so it will not affect really too much mobility. And indeed, we found a mobility of 30 centimeters square per volt per second, which is a typical mobility that has been reported also in previous work on printed graphene films. And of course, in order to reduce the sheet resistance to 2040 ohm per square, we had to anneal at 400 degrees C. However, Mark has introduced photonic annealing yesterday, and I want to mention here that we have indeed preliminary results where post-processing was done with on our films with photonic annealing, and also in our case we basically observed that it's possible to decrease the sheet resistance by using photonic annealing down to 2040 ohm per square without damaging the paper. So this is a great technology to perform post-processing on temperature-sensitive substrates such as paper and plastic. Okay, so then with those inks, we started to fabricate a fully printed heterostructure, and the first device that we made was a photodetector, and this is a 3-layer heterostructure. We have 2 graphene electrodes, one at the top and one at the bottom, and in the middle we have the printed photoactive film, which was made of tungsten disulfide ink. And initially we printed on silicon. And with the inkjet printer, it is obviously very easy to print many devices in one go. And actually, this is a requirement in inkjet printing. The yield is very important. And so because of that, we started to print arrays of heterostructures. So basically, something that looks like this. And in this picture here, I hope you can see there are some black lines, horizontal and vertical. So these are the top and bottom graphene electrodes. And then in the middle of each junction, there is this yellowish, greenish square, which basically correspond to the printed tungsten disulfide film. So in the case of silicon, we printed a 10 by 10 arrays. So we printed 100 of those heterostructures with the same ink, with the same cartridge, all in one go. And we basically characterized all of them. And it turned out that none of these heterostructures is actually shortcut. And this is what was a great result, because basically the thickness of the tungsten disulfide film is around 200 nanometers. And so if we would have intermixing at the interface, then the graphene from the top and the bottom will actually diffuse into the middle layer and will cause a shortcut of the device. But none of our devices was actually shortcut. And the IV characteristic of all the devices were basically the same with an experimental error. So on silicon, we really achieved 100% yield with all reproducible devices, which again show that our inks have been properly modified and engineered for fabrication of heterostructures. Then we repeated the same type of arrays on plastic, as you can see here, and we studied the changes in photocurrent under bending condition. And as you can see, the device is basically stable up to 2% of strain. Unfortunately, our setup doesn't allow us to probe higher strain. And then we moved on to paper. And on paper, we try to optimize the photoresponsivity of the device because, as I mentioned before, paper allows us to minimize the sheet resistance. And so in this video here, you can see this pink line, which is the photocurrent that is generated every time we illuminate this piece of paper where we have the printed photodetectors with the light of the microscope. And you can see that the photocurrent goes up and down following the switch on and off of the light on the microscope. And since we started to do this kind of arrays, at a certain point, we realized that we don't need to necessarily repeat the same device in each junction. And so, for example, let's have a look at this picture here. You can see that we have 1, 2, 3, 4 junctions. And in 2 of the junctions, we actually printed the heterostructure that I showed you before, which from an electrical point of view is a double diode. But then in these other 2 junctions here and here, we decided not to print the semiconducting layer. So effectively, we have a shortcut. So now we have 4 junctions where we have 2 different electrical components, the shortcut and the double diode. So if we now apply a bias between the top and the bottom graphene electrode, then the signal that we can read here in each junction will be different depending on the electrical component that we have. So this is a very simple way to actually generate a binary code, which can be read, for example, by connecting each junction to an LED, as you can see here. The LED will switch on or off depending on the electrical component that we have by allowing us basically to read the code. So we call this device a read-only memory because basically it allows to generate a binary code and which can be, for example, used for identification purposes. And is read only because obviously once the device is printed, the code cannot be changed or erased. And the code, however, will be only known by the people that are designing actually the device. So moving next, as I mentioned to you, our final goal is to produce a fully printed integrated circuit, and to do so, we also need obviously transistors and diodes, but we also need the passive components such as capacitors. And capacitors are very easy to make because our exfoliation approach also works with hexagonal boron nitride. And so we can get highly concentrated dispersions of hexagonal boron nitride in water that can be implemented into the heterostructure. So the capacitor has exactly the same structure that I showed you before for the photodetector, the graphene at the top and at the bottom, and then we replace the boron nitride ink with the tungsten disulfide. And because we're using a Ninja printer, we can change the area and the thickness of the capacitor as we want. So we can span a very large range of capacitance, and we can even connect those capacitors that you can see here in parallel to further increase the capacitance with the Ninja printer very easily. And so in this way, we've been able basically to fully characterize the electric properties of this boron nitride ink. And so we know the electric constant, the breakdown voltage, and so on. And if you look at the numbers that are reported down here, you will see that actually from a dielectric point of view, this boron nitride ink is extremely good. It's quite comparable to silicon oxide. And so it can be used as a dielectric for devices. And not only within 2D materials-based electronics, but more in general, we can also use it for in combination with other nanomaterials or with other technologies. And I will show you 2 examples of what I mean. So in the first example, we basically collaborated with Aaron Franklin at Duke University, and he's an expert on printed transistors made with semiconducting carbon nanotubes. And we implemented our boron nitride inks into the device fabrication. And basically, Aaron was able to demonstrate that it's possible to produce a high-performance device by fabricating the device completely under the inkjet printer. So typically, the device will need to be annealed or washed and so on. All these processes are being made by using the capabilities of the inkjet printer. So annealing will be done, for example, by increasing the platen temperature, which can go up to 80 degrees maximum. So the fabrication of this device is done under very restricted conditions, under a maximum processing temperature of 80 degrees C. And despite that, the device, if you look at the trans characteristic, is actually showing very good performance, very good mobility, very high on-off ratio, and very important, very small hysteresis. And this is enabled by the use of materials that have very good performance even under such a low processing temperature. And this was a problem in the past for Aaron. He tried different type of dielectric materials, and they were always failing every time he was trying to produce the device in these limited conditions. But our boron nitride, actually in combination with the semiconducting carbon nanotubes and metallic nanowires, demonstrated the ability to produce very high performance devices at a maximum temperature of 80 degrees C. And clearly those devices can be made on paper, on plastic, and they are suitable for flexible electronics. In the second example, we actually decided to combine CVD with inkjet printing. So as you know, CVD, chemical vapor deposition, allow us to produce 2D semiconductor materials with of very high quality. And so we said, okay, on one side we have these very high quality semiconductor materials, and on the other side we have the all the other elements that are needed to produce transistors by inkjet printing. So why we don't combine the two of them, and we establish a sort of hybrid technology? And so what we did in this work was to pattern the CVD molybdenol disulfide into stripes and transfer them onto paper, as you can see in this picture here. And then the rest of the device, the electrodes, the electric and the top gate were done using the boron nitride and either silver or graphene inks. And with our surprise, it turned out that the fabrication of the device on top of these very high quality channel actually does not affect the electronic properties of the channel. The mobility is still very good, and the on-off ratio is still very high, and basically those values are comparable with the same mobility and on-off ratio that one will find by basically making the same transistors by standard lithography. And the beauty of this process is that the channel is down on a piece of paper. So its position is fixed and is in the form of this very long stripe. So what we can do by inkjet printing very easily is to make several transistors along the length of the stripe, as you can see in this picture, and connect them together very easily with the inkjet printer to produce more complex circuits. So, for example, in this work, we demonstrated high gain inverters, logic gates, and current mirrors on paper without any post-processing. Of course, the inks can also be used to make printed sensors. We have already demonstrated photodetectors, but we can also probe strain, humidity, and so on. And because they can be printed on paper, they can be combined very easily with the printed RFID. These are typically printed with the silver on paper. So that means that we can basically make a wireless sensing platform completely printed on paper. And this is actually what we've been doing in collaboration with Professor Zirong Hu at the University of Manchester, who's able to screen print the graphene RFID antenna. So here, for example, you can see the wireless reading of the temperature inside this box. So this is the RFID. And so if you can heat up inside the box, then you will be able to read the changes in temperature in a wireless way. And the same can be done for strain, for example. You can read the changes in the strain through the changes of resistance of the sensor by using a mobile phone. And in the last few minutes of my talk, I want to move into biomedical applications. Indeed, I told you at the very beginning that we didn't want to use an NP because it's toxic. But at the end of the day, you can see that we have used many additives into our ink, and in particular, we have used pyrene derivatives, and the small aromatic molecules are very well known to be toxic. And therefore, we decided to perform a cytotoxicity test. This was done in collaboration with Costas Costarelos at the University of Manchester, and so the inks were exposed to 2 cell lines at different doses, and the results indicated that basically all the inks, no matter the 2D material that we consider, are actually biocompatible. And these results were actually very interesting because not only the cells do not die, but we observe a very strong cellular uptake, meaning that the material can penetrate the membrane. And so this opened up a possible use of our inks for drug delivery and related applications. So we started to look into the field. Obviously, this is something completely new for me. And we realized that typically cationic nanomaterials are preferred for this kind of applications because they can better interact with the negatively charged membrane. And in our case, however, our materials are all negatively charged because the surface charge is given by the sulfonic group. And in principle, we could simply change the pyrene derivative and to change the surface charge of our dispersions. And in practice, this is not so simple because exfoliation with pyrene derivatives is not fully understood yet. And so we know that certain pyrene derivatives are working well, others do not work at all, and others are able to exfoliate, but usually in producing low concentration or weakly stable dispersions. And so because of that, we decided to work together with the organic chemist in my department and to start synthesizing from scratch different pyrene derivatives in order to produce graphene dispersion with specific surface charge and chemistry. And so, for example, we investigated the use of amphoteric pyrene derivatives and in order to change the charge of our dispersions. So the exfoliation is done in neutral conditions, and after that we basically change the pH in order to change the surface charge. And in the case of the pyrene functionalized with lysine, we actually have been able to cross the charge neutrality point and to produce both positive and negatively charged dispersion, however, those have been achieved at very high pH, which are not suitable for biomedical applications. And so I'm about to finish. And so we decided, therefore, to use cationic pyrene derivatives. And here the chemists did a great job. They changed the functional groups and the distance between the functional group and the pyrene core. And this was a huge study that really allowed us to understand, or at least get insights on how to design the pyrene derivative to achieve the highest yield and stabilization. And I want to mention that because my time is almost over, that actually the cationic graphene dispersion that were produced with these pyrene derivatives were all biocompatible and they did show indeed very strong cellular uptake, even better than the anionic ones as expected. So we are now developing possible biomedical applications with this material. And with this, I want to mention that we have quite a lot of works coming out soon, and one is actually has been already published in Nature Nanotechnology, where our inks were used to make viscoelastic electrodes for soft tissue, and I will invite you to read this paper. And with this, because my time is over, I want to thank all the people involved in this work and you for your attention.
Great, thank you. We probably have time for one or two quick questions. Let me just ask, you've produced a lot of technology. Do you patent these things? How do you interact with industry? What does your university allow you to do?
Okay, we actually have 3 patents, and I have another patent also in collaboration with HP, which funded part of the results that I showed today. In terms of industry, I guess you are aware that we have the National Graphene Institute and the Graphene Engineering Institute in Manchester. So all the interaction with the industry is basically collected by these 2 institutes and then passed down to the basically academic people.
Very good. With that, I'd like to thank Professor Cinzia Casaraghi one more time and congratulate her on the well-deserved Alan Heeger Award for Outstanding Young Investigator.
Thank you.
Our next speaker in the session is Professor Jeff Zink. He's a distinguished professor in the Department of Chemistry and Biochemistry at UCLA, University of California, Los Angeles. He's among the world's most highly cited authors, according to Clarivate Analytics. And he's done some amazing work in recent years where he's looked at how to take drugs and other things and encapsulate them, and then how to release them under very controlled conditions. And this morning, he's going to tell us about his work on stimuli-responsive nanoparticles and nanomachines for biomedical targeting, imaging, and drug delivery. And I'm proud to call him my senior colleague. Jeff.
Thank you, junior colleague. I appreciate the introduction. Yeah, so Rick already gave you the title. And what I want to emphasize today are going to be how we can stimulate controlled responses from the nanomaterials I'm going to talk about. My primary affiliation, as Rick said, is with the Department of Chemistry and Biochemistry. I'm also co-director of the CMIN program of our Comprehensive Cancer Center. So I'm the nanotheranostics NT part of it. And I'm affiliated, of course, with the California Nanosystems Institute, and I wish we could all be together there.
Jeff, could we get you to hit the full screen button?
Okay, if I can find it.
Yeah, the little green one on the top left.
It says you are screen sharing.
Right, it's screen sharing. We're just trying to get the full size. We can see it. It's good. It will work. If you see the little green button on the top left, if you just click on that, you're close. A little bit further left. Yeah, right up there.
It says mute. Oh, up there?
Yeah, that one.
Okay.
Yeah, that did it. Thank you. Yep, perfect.
Thank you, Rick. Okay, so the main application in our research is to trap molecules inside of the nanocarriers, carry them to the site of a disease, such as cancer, intercellular diseases, with no leakage to avoid off-target effects. We can locally release a very high concentration of the drug, release only on command. And this is the key part of it. We can either use signals from the disease itself, or we control it externally. And that's mainly what I'll be talking about today, how we can externally do the controlling, and then we can kill the cancer infectious agent. So what I would like to do today is to begin with just a small background, very brief background on template silica and the biological applications. Then I briefly want to introduce those autonomous machines, machines that can work in biological systems with no external intervention, primarily by pH and redox processes. So I'll very briefly mention those. Then the main part of my talk will focus on external activations, magnetic field activated particles. The magnetic fields penetrate tissue. We can go all the way through the body. So I'll describe how we do that and can deliver therapeutics. And then most recently, we've been working on high intensity focused ultrasound, or HIFU, inside of an MRI for image guided therapy. So those last two will be the main features of my talk towards the end. Okay, silica that we make is done by what's known as a sol gel process. This is over a century old, in the 18th century from France. Hydrolysis and condensation of alkoxysilanes can produce SiO2 or silica. If it's done in acidic conditions, which is what's drawn here, you can make beautiful little monoliths, thin films, and so on. And those were the initial aspects of our discussion. If you use basic conditions, under very controlled conditions, you can make nanoparticles, and that'll be what we're doing in our talk. Now, several decades ago, people in an oil company made MCM41. They use surfactant templates. These templates can go through a variety of liquid crystalline phases. We're most interested in that hexagonal structure, 2D hexagonal structure on the right. And if this process is coordinated with the sol gel process under proper pH conditions and so on, one can make mesoporous nanoparticles. And these are nowadays very well known. They have incredible properties in interior surface areas of 10 to the third square meters per gram, pore volume, large enough to carry many, many drug molecules. And these are biocompatible, and they are in being extensively studied all over the world today. So it's these types of particles that we're going to use. We like them very much because they're very easy to derivatize. So by using alkoxysilanes, as shown on the top part of this slide, one can easily attach anything you want to the hydroxyl groups, the SiO minus groups on the surface of the silica. And then the R groups here, some of them are shown. We can link up just about any molecule, including biomolecules, enzymes, antibodies, and so on and so on. So the chemistry for attaching things to these nanoparticles is really rather straightforward and very, very versatile, which makes this a very good platform for studying. Now, one of our first areas where we studied this was using the mesoporous particles, nanoparticles shown here. We showed that we could, in one type of particle, achieve multiple functionalities. So what we've shown here is a particle that's been grown around another nanoparticle. We'll be using superparamagnetic particles for our magnetic heating studies. I'll talk about it a little bit later. So that's one functionality we can use. The porosity, of course, is there to be able to carry the cargo molecule in the pores. I already mentioned that we can attach almost anything we want, including targeting ligands for particular cells, nanomachines, and so on and so on. And all of these can be done on one particle. So this versatile sort of structure allows us to have a big field where we can devise all sorts of different useful materials. The types of materials I want to talk about today involve nanomachines. We fell in love with supramolecular nanomachines several decades ago. And the two that I'll be talking about today and used for a variety of different things are the two on the upper right, the so-called snap-top and the so-called nanovalve. And these are the two that I'll take a look at because they've been used in vivo in mice systems and they function very nicely. The definition of a nanomachine that I like to use, the dictionary definition, that has a solid support, moving parts, and accomplishes a specific objective. So, and of course, any nanomachine requires a power supply. So our system, then, solid support is silica. The moving parts I'm going to describe to you as we go along. And our objective, of course, is to trap drug molecules, for instance, therapeutics for biological applications, trap them and only release them upon command. That's the objective. And all nanomachines require power supplies. How do we operate these machines? How can we make them work under these conditions? So the power supplies are shown here. We can use either internal stimuli, stimuli that occur in the biological system itself. And so redox, antioxidants, for example, in cells can be used to stimulate machines. Glutathione is an example. pH changes as you go from the blood, pH 7.4, to the more acidification in lysosomes and endosomes. That pH change can be used. Those are the two I'll talk about today. And enzymatic interactions, of course, specific to particular types of cells, can also be used. Externally, which will be the main part of my second part of the talk, the three main ones are light, magnetic fields, and ultrasound. Light has beautiful spatial location, but it doesn't penetrate very far. Magnetic fields have the least spatial configurations, but specifications, but they penetrate everything very, very deeply. And ultrasound is kind of in between. It penetrates most tissues, and it can be focused, as I'll describe. So first, let me just very briefly describe to you a couple of the internal stimuli that have worked under biological conditions. So pH stimulation and redox stimulation, as I mentioned, are the two that we've used in biology. And our applications in mice have been to cure intracellular infectious diseases. That's what I'll mention today. And also to treat ovarian cancer and triple negative breast cancer with colleagues at the cancer centers. So I'll talk about now very briefly the pH and redox stimulated systems. Our nanovalve I'm going to show you is the pH stimulated one. The nanovalve consists of a mesoporous silica particle shown in part A and B there. The pores are illustrated. They're loaded with drugs by soaking the particles in the solution of the drug molecules, yellow balls. And then these stalks on the surface are attached to cyclic capping molecules. So these are the supramolecular forces that I mentioned briefly. And then under the stimuli, in this case pH, the cap can be stimulated to come off, that opens the pores, and the drug molecule can come out. So that's an example of a nano valve. Here's the one that has been most useful biologically. This very simple valve consisting of a benzimidazole molecule with a beta cyclic electron cap. So there's a cyclic cap and the stalk. Those are attached to the surfaces of the nanoparticles, including around the pore entrances. when the benzimidazole is in the neutral form, is drawn here. It's hydrophobic. The hydrophobic interior of the cyclodextrin joins to it by supramolecular van der Waals forces and so on, hydrophobic forces, and the system is stable. But under acidic conditions, you can protonate the nitrogen on the stalk. That makes it hydrophilic. Therefore, the cap comes off, and that can open the pores. So the system works very, very beautifully. At pH 7, the pH of blood, the pores are closed, and no drug molecule, in this case doxorubicin, can come out. As we go towards the pH that occur in lysosomes and endosomes, 6 and 5, you can see that the system starts to release the doxorubicin because the cyclodextrin caps have come off. So this works very beautifully under physiological pH conditions. The second one that works very beautifully is what we call a snap tap. The original one was based on this kind of capping, like a Gold Spear bottle has, where some kind of stopper holds a plug in place. So this again is a cyclodextrin that's held in place by a cleavable stopper. And when that is broken off, like opening the bottle, the cap comes off and you can release the drug. Now, a much simpler way of doing that is to break the stalk directly. So if we have disulfide bonds, which is shown here, under redox conditions, under reducing conditions, that disulfide can be broken, the cap snaps off, and it releases the drugs. So it releases the caps and the drugs. And so glutathione, for example, is the most common antioxidant in the cells that is involved with this process. And we were very successful using these in vivo in mice to treat both cancers and infectious diseases. I like the infectious disease because it's easier to illustrate without showing a lot of dead mice. So what I show here are confocal images of white blood cells that have been infected by bacteria. And the one on the top was infected by M. tuberculosis. This intracellular bacterium gets taken up by the white blood cell, as it should be, but instead it hijacks the cellular machinery, actually grows, replicates, and then eventually the cell dies. It's very difficult to cure because it's in the immune system. This one on the bottom, F. tularensis, is a tier 1 select agent of bioterrorism. It's a biowarfare agent, basically. And again, it's very, very infectious. It goes into taken up by the cells, and it grows in the white blood cells. So what I show here now is that our particles loaded with DOX, which are all the red in the image, are endocytosed by these phagocytosed by these white blood cells. Many, many, many particles get inside a particular cell. Now they're right where the bacterium is located. It's very easy to kill it, and we can cure the diseases. So the disease that's most important in the world that we're working on is tuberculosis, and you can see that it's very, very infectious and kills a lot of people. The disease that brings us the most money is bioterrorism diseases. The DoD wanted us to be able to protect soldiers and civilians, of course, from F. tularensis, which is highly effective. So those are examples then of the systems that have worked in vivo. And just to give you one idea of the kinds of things we study, we take a look with my colleagues, lung, liver, and spleen, which is where the disease occurs. And by delivering our particles, we can decrease the colony forming units. We can cure the mice of these diseases. So this is an example then of intracellular things happening. No external control. It's just the control by chemical energy inside the overall cells. Now I'd like to turn the rest of the attention in my talk to the external control of drug delivery. And of the big three that I mentioned before, alternating magnetic fields and ultrasound are the two that we're most heavily focusing on in our research right now. Both of these are non-invasive. They're harmless under most conditions to organisms, and they totally penetrate the organism. So they're potentially very, very useful for biological systems. I very recently wrote a perspective for JCS. The reference is shown here, and our thoughts on the external control of nanocarriers for theranostics is kind of summarized in that article. Okay, I'll begin with the alternating magnetic field stimulation. So now we're going to take a look at nanoparticles, multifunctional particles that have cores. So the TEM image on the right is an example of a mesoporous silica particle with a superparamagnetic core. I'll define those a little bit more detail as we go along. And you can see the structure of these is slightly different. The pore structure is radial. It radiates outwards from the center, but it has the same sort of properties I've already mentioned: a very high surface area, a very high internal volume, and it is very, very useful, as you'll see. Now, the method for using the alternating magnetic field is to generate heat from these internal cores. So superparamagnetic cores in the presence of the alternating field heat up. And what we need then is going to be thermosensitive caps that will respond to that heat, which will then open the pores and release the drugs. So that's going to be the overall goal now and focus of the things I'm going to tell you about. Thermosensitive caps on these types of core shell nanoparticles to release the drugs. Okay, the first thing we need to do is make the particles. We want to get the maximum heat. So one of the types of particles very similar to Fe3O4 spions, which are the most commonly used in biology. These are doped materials which have much higher magnetization. And superparamagnetism is shown in figure C here, where you can see that there's no hysteresis as the magnetic field is increased and decreased. So the entire magnetic particle is one domain. All the spins line up the domain, and you can get very high magnetizations. And then when you apply the magnetic field by mechanism I'll describe next, that interior core can heat up. So we do show here how the temperature of the whole bulk solutions can be heated under very high fields. And from that, we can measure the amount of heat generated by the particles for certain conditions of the magnetization and control it. Okay, so that's the core that we're going to be using in these studies. Now, the biological applications aren't a dream. They're actually being used. The primary use of these sorts of things is hyperthermia. That means taking advantage of the high heat. And this therapy has been approved in Germany. It's being used in the clinic. And there's a lot of clinical trials going on in our country. And this type of hyperthermia is quite useful. For hyperthermia, we want to get the maximum amount of heat, raise the temperature of the tumor, for example, and just basically kill the tumor by the hyperthermia. So that is not a dream, that's real. Now, in our goal, we want to control that heat because we'd rather induce apoptosis rather than necrosis. We'd rather release a drug. We don't damage too much tissue, but we can do both, of course. If we just crank up the field, we can get more heat. But I'm going to show you how we can actually more precisely control the temperature and control the amount of drug that can come out. There's two mechanisms that are operating, that can operate, I should say, in the presence of an oscillating magnetic field. They're called Néel relaxation and Brownian relaxation. So this is how the heat is generated. How does this occur? In the case of Néel relaxation, as the alternating magnetic field operates, that's the green arrow on the far left, the electron spins in the domain follow that field. And under the high frequency, we're using alternating fields. Under high frequency alteration, there's a hysteresis developed, and that deposit generates heat inside the particle. So heat from the electron motion is what's called Néel relaxation. That's one of the two mechanisms. The second one is what's called Brownian relaxation. And in this particular case, the spins are locked into the crystal structure and the entire structure moves. So in this particular case, it's more like a frictional heating. It's the motion of the particle itself. And that's called Brownian relaxation. And that's the second mechanism that can operate. In macroscopic systems, hysteresis induced electrical currents, eddy currents, cause heating. And that's commonly used in industry for heating big pieces of metal, but it's not relevant to the system that we're using here. Now, we were very interested in determining what mechanism we have. We want to know if our particles are moving or if it's just the electrons that are moving. A way of doing that is to use fluorescence depolarization. This is an optical technique. And basically, the idea is if the system moves, the photon comes in, if the system moves, the direction of the polarization will also change. If the system is static, the polarization won't change. And that degree of anisotropy, R, the difference between the parallel and perpendicular light, is a measure then of how much motion there is. So a decreasing R means fast particle motion under the alternating magnetic field. It's that would be the motion of the particle causing the orientation to change. So we measured that. We doped the magnetic parts with europium-2, so we were able to get an emission, a red emission from that. The mesoporous particles themselves have a blue emission from defect centers, dangling Si bonds in the silica matrix. That has a blue emission. And so we had two different bands. We could look at the core and we look at the shell. They overlap a bit, but we can choose regions of the spectrum where we primarily core, primarily shell, and we could measure if there's motion. And so we did those experiments, and we found that in everything that we measured, in the presence of the magnetic field or in the absence of the magnetic field, there is not Brownian, no change really in the motion of the particles. So in our case, Brownian relaxation is not the major contributor. It's primarily the electron motions. This is a very sensitive technique. We can look at the difference in viscosity between cyclohexane and hexane, for example, and see the changes in the motion. And we don't see any changes in the magnetic field. Okay, so the particles basically are static. It's the electrons that are moving. So we're not going to be ripping apart cells when the particles are inside because the particles are spinning or something. Okay, now how much heat can we generate? So for these particular studies, we took a look at the temperature. So we made a little nano thermometer. It's a yttrium fluoride doped system. And we're able to put that nano thermometer in the same nanoparticle as the heater, the superparamagnetic particle. So we were able to make silica particles that contain both of these components, the heating component, the supermagnetic particle, and the optical thermometer. And we characterize, and you can see that we have the iron and we have these yttrium in the different places. The particle, we do have these dual core shell particles. The thermometer works because two excited states are in near Boltzmann equilibrium with each other. So the ratio of the populations of those states is going to be related to the temperature. We can look at the emission spectrum and get a working curve, put them in known temperatures and look at the ratio of those. And from that working curve, determine the temperature inside our nanoparticles. And when we do these experiments, we find on the right-hand side of this thing, the bulk solution, of course, does heat up, but the internal temperature is much higher than the overall bulk temperature. And that's going to be a key because we can use that local nano internal temperature on the particle to release caps without necessarily overheating the overall bulk system. So we were able to show then that we are we were able to show that we're getting heating. Of course, the operation of polymers and others caps in the presence of the heat also prove that the systems are heating up. That's how we can measure the temperature. So now we have an idea on how much we can do. The final step is to use a thermal responsive cap to be able to cap and release. And we have a variety of these sorts of caps that can be used. One of the early ones that we looked at uses the retro-Diels-Alder reaction. Diels-Alder reaction is thermosensitive. So at low temperatures, we could put a very bulky adamantane cyclodextrin type cap on the whole thing. That's just a big capping system. But under higher temperatures, the retro-Diels-Alder breaks that bond. It's a snap type, if you will. The top comes off and the drug can be released. So that was one of the early types of caps that we used. A second type of thermoresponsive coating, and this again involves, this for the first time now, involves a polymer, is we use the polymer shown on the bottom left there, which has these azo bonds. This molecule is used when you heat it up to make radicals. It's a radical initiator for polymerization. In our case, we just wanted to look at the bond breaking as the nitrogen gas comes off and the whole polymer breaks up. So we attach both ends of this polymer all over the place on the surface of the particles. It's everywhere. It makes a big mess of polymers on the surface. And if we do that after we fill the pores with the drug, we're able to trap the drug. And then if we put it in the alternating or oscillating magnetic field, the internal heat breaks those bonds that causes the polymer to disintegrate. And of course, as the polymer comes off, it opens the pores and we're able to deliver the drug. So that was another early type of cap that we used. For our supramolecular systems, very, very early on, we used this particular type of thread cyclic molecule motif again. In this particular case, the cyclic molecule is cucurbityrol, and the thread was this diamine system that's shown on the lower left. And this particular capping is, of course, thermosensitive. The binding is pretty good at lower temperatures, but as you heat it up, you get a bond breaking. And indeed, that works. The cap comes off, and we could release drugs. And in this particular system, I should go back once if I can. In this particular system, we were able to do this in ice water. So we were able to show that without any external heating at all, just that internal heating, we could release the cap. So that was a test to show that we have control as we wish over the release of the drug. And finally, the one we've been using mostly now, again, involves this azo type group in the center here, where the bond thermally breaks it. And here is another snapshot. We just attach a big bulky system, as shown in the overall right there, onto the system. When that bond breaks the very far right, then that big bulky cap just breaks off, and we can release the drug. And this is our most active one right now. Wei and Xiancheng invented this particular system. So those are a bunch of thermosensitive caps. Now, what can we do with these? Well, and for this last one, the bond is caused by heating. Bond breaking is caused by heating. So we can, of course, show that just by heating it in the water bath, and we can demonstrate that there is drug release. So that works very nicely in a hot water bath. We could demonstrate that with a probe sonicator, not any HIFU, but just ordinary sonication, and that shows that that could work. And then we were able to show that with high-intensity focused ultrasound, excuse me, I'm on the wrong subject here. This also works with ultrasound. With the heating from the magnetic field, then can cause it to open. And depending how long we turn on the magnetic field, very short amount of time or longer and longer, shown as B through F down in the bottom here, we can get more and more drug release. And on part G on the very, very lower right, we can measure the overall temperature in the bulk system as we do this. And so you can see then that the maximum bulk temperature rise is only 4 degrees centigrade as we do this for the longest magnetic field on part. But we can get very, very good release very, very quickly. So here we're able to control then the overall temperature and not damage tissue if we don't want to do it. Of course, we turn it on longer. We could if we wanted. And we can control the dose. The amount that comes out depends on the amount of time that we've had the magnetic field on. So here we have dose control and drug release by a magnetic field that totally penetrates the system. We've done this in vivo, but we haven't published it yet. Our in vitro study in cells is shown here. And the bottom line for this particular system is that we can demonstrate that the cells are undamaged by the ultrasound, by the magnetic heating, whereas the drug is released and we can kill the cells by drug release. So this is a demonstration then of how we can develop a very good control over the whole system and do our drug release. Okay, I've been saying ultrasound. So the final thing I want to talk about now is ultrasound. And so what I'm going to show you here now is how we can use, again, a tissue penetrating stimulus. This particular ultrasound, I'll give you the specifications just a second, can be focused down to a few millimeters. I'll show you how that is done. So we do have spatial control, and we can use that, as I'm going to show you now, for cargo delivery. And all of the experiments I'm going to show you are done in a patient-ready MRI scanner. Instead of a patient, we put what is called a phantom. That's the term that's used, which is a agarose gel, and the sample is in there. And so under direct MRI imaging, we simultaneously can use ultrasound and deliver drugs. Now, this system is used in the clinic to treat fibroids in women and prostate cancer in men. So these techniques are clinically approved, and we're going to adapt them now for overall drug delivery. And so what the little sketch here shows that because it's focused, we can precisely deliver drugs where we want, when we want, and see what we're doing as we do it. Okay, so this is going to be now HIFU external stimulation. The HIFU that we use is shown in the overall left here. The focal point is about 0.7 by by 3 cubic millimeters. So it's not as focused as a laser would be, but it's fairly highly focused. Our frequency is 2.5 megahertz and our power range is 18 to 24.5 watts. This is the clinically used HIFU system I'm describing here. And that is just placed under our phantom. And the focal point then is where the HIFU with ultrasound is going to control the nanoparticle. So how do we do that? We need to have now a ultrasound responsive cap. And the simplest one that we use is a PEG cap, a PG, probably I think like a biocompatible. And in this particular case, we were able to show that we and others have done it, that ultrasound can actually break apart the polymer. So we showed that the polymer is intact as a capping agent. In the presence of ultrasound, the cap breaks apart and HIFU simulation breaks it apart, and we can release the drug. So that's our very simple capping system for this particular experiment. We did mass spec to prove that the system is falling apart, and there is some details involving the ultrasound here. As we can see on the right-hand side, here are some MRI images of our effect of our sonication. And as in this case, we're releasing gadolinium and changing the overall contrast so we can see how much has been released. And it works in the ultrasound system. So again, this is what we do. We place the Agros Phantom on top of the HIFU transistor, exactly as it's done it with the patients. And then we're using a 3 Tesla whole body MRI scanner. It's a Siemens instrument, and that's the way we do the experiment. So here we show now our phantom with a variety of sample wells. We put our sample, in this case, it's our nanoparticle with gadolinium in it. We stimulate it with the HIFU, and the middle one shows the focused high-intensity ultrasound focused in the middle of our sample system. And this is what you see there is an MRI image. You can see where the focal point of the ultrasound is located is where we see the huge change in contrast, and we can measure it. We can also, let's see if I can go back here. So we have three-dimensional control of this. So here you see the 3 different views, axial, sagittal, and coronal views. You can see from these that we have a very localized direct release of our cargo. And so we're going on. We were expected to start our mouse studies this week, but the scanner broke. But we're soon going to be doing this in mouse and show that we can directly deliver a drug. In our case, we're going to do a pancreatic cancer drug, directly release it under MRI control. And it's our nanoparticle then that allows us to carry out the overall therapy. Okay, we've done this already now in tissue, so ex vivo, so to speak. We go to the grocery store and buy a chicken breast as shown here, or we can buy steaks. And so we can actually test this in tissue before we actually get into the mice. We can do this direct delivery in tissue. That just is another preliminary experiment. And as I say, we'll soon be doing this in mice. Okay, the final thing I want to mention, and I'm close to running out of time, but is we can also use HIFU for something else, and that is as an imaging device. And so here we're using just the inverse. We want to be able to modulate the magnetic response and basically use a lock-in amplifier or a boxcar type integrator to increase the overall signal and increase the imaging abilities. So very, very briefly, in this particular case, we use a HIFU sensitive polymer that can spinipam. And here it's probably the temperature increase of the HIFU that is causing the effect. But under lower temperatures, you can go on higher and low temperatures, you can either have the polymer open hydrophilic or closed hydrophobic. And what we're trying to do here now is attach gadolinium inside and change the water axis. The change of the water axis will change the contrast. And if we can do this repetitively, we can amplify that overall signal. So we showed then that in fact the T1, and this is now using the MRI to get these values, we showed that we can actually change the value of T1. Simultaneously, the MRI can measure the temperature. I didn't mention that, so we can actually measure the exact temperature at that focal spot. The temperature rises and decreases, that's shown on the right. And the overall intensity that we see in the MRI image is shown in the bold black on there. So we can actually modulate it. So what we do here then is we turn the HIFU on and off. We get this modulated T1 signal. And then the Fourier transform of that signal gives rise then to a signal that is essentially amplified. It's looking only at the noise, is the signal's noise ratio increases, just like as you would in a lock-in amplifier. And when we do that, then we can very, very strongly amplify various regions. And so we're going to use this to look for tissue margins, the cancer tissue margin between the healthy tissue, and also look at very small metastases that are present when we can target this kind of system. So this kind of spotlight using the MRI, using HIFU to scan in the MRI and find particular tissues, I think is going to be a very, very powerful technique. And here we show in our published paper, we were able to get an 83-fold enhancement in the overall contrast of the system, the overall image. And our current record right now is 116-fold enhancement. So this is going to be a very, very powerful technique for us in terms of enhancing images. This can be done in 80 seconds so that it actually can be useful in the clinic. The patients are usually in for 20 to 30 minutes. So we think that this is going to be a very, very useful system to find metastases. Okay, so to conclude, I just would like to remind you then that I told you about nanomachines and specifically snap-tops and valves that we tested. I showed you how we can use autonomous signals from the cell itself, pH and redox, to stimulate these machines. I've shown you how we can use magnetic fields to change the temperature and activate thermosensitive caps and deliver drugs. And in our case, we've shown that in cells in vitro. And I've shown you how HIFU can be used in an MRI to release drugs and also to amplify signals. And in all these particular cases, high local concentrations of drugs can be released when and where we want them without premature release and hopefully avoid off-target effects. So the people who did this are shown in these slides. The magnetic ladies who did this, Feng Shi did the nail studies. Jiao Dong did the thermometer studies, and Tian did the HIFU studies. Tian was mainly involved with the amplification. Wei was mainly involved with the magnetic heating. My colleagues, Holden Wu in radiology, he handles the MRI, and my colleague Marcus Horowitz in medicine, infectious diseases were important to us. And of course, the funding from UCLA and various organizations was very much appreciated. So on that note, I thank you, and I'll be happy to take questions.
Thank you very much for a very stimulating talk. If there's questions, you're welcome to unmute yourself or send them via chat. There is a question in chat. It comes from Sergey Nikotenko at CNRS. He says, thank you for your talk. Is it possible using AFM and HIFU stimulation simultaneously? Could there be some synergy reached by using them both?
The answer is yes, but not in an MRI. The HIFU it doesn't have parts that can be used in the MRI, but of course the magnetic nanoparticles would be attracted to them by the magnetic field. But otherwise, yes, if you don't want to do it inside the MRI, then indeed one can use both the magnetic fields. The magnetic field is done in a simple spiral of copper. It's about 5 centimeters in diameter. You can put a mouse in it, and you could also then, of course, direct HIFU into the center of that magnetic field. So that's the long answer. The short answer is yes.
So another thing, you talked about using paramagnetic particles. I'm curious what would happen if you use ferromagnetic particles. Is there a particular reason for the size of the paramagnetic particles?
That in principle can be used. Yes, the key feature is the magnetization that you can achieve in the particle, because that's what interacts with the oscillating field. So the higher the magnetization that goes as a square of the magnetization, the higher the magnetization, the more heat you can generate. So we're using the super paramagnetism because that's the entire domain is in one particle, and that's really the nanoscale. So, but the answer is in principle, any ferromagnetic will heat up, and the question is how useful, how much heat can you get, how useful will it be?
Very good. Anyone else? All right, with that, let me thank Professor Zink for a very stimulating talk. And this will conclude our keynote session for this morning. I also want to again congratulate Professor Cynthia Casaraghi on her well-earned Heger Award. So thank you all, and we'll head back to the regular sessions now.